In this video, we will address the following question. How can we design our intelligent system when the hardware layer is a data center? In other words, how can the presence and availability of such a large-scale and high-performing computing infrastructure affect the design and development of the software layer and the AI application? From the hardware point of view, data centers comprise racks and servers for computation, for storage, and for networking. Parallelization and scalability are crucial abilities to support the learning and inference of machine and deep learning solutions. Here, high-performing CPUs as well as hardware accelerators, for instance GPU, TPU, and FPGA, are relevant technological assets. In addition to computation, high-performing storage and networking solutions, such as networked attached storage or storage area network, are crucial to overcome one of the main bottlenecks in the training of large neural networks, which is the need to move large quantities of training data. In a data center, the middle software layer comprises three different modules: the virtualization layer, the computing framework, the machine and deep learning framework. Let's start analyzing the first one, the virtualization layer. Its aim is to virtualize computing, storage, and networking resources present in the data center. This ability is crucial to support the cloud computing paradigm, where hardware resources are made available in an online and on-demand manner to users. This ability is also crucial to support the as-a-service approach in machine and deep learning, where virtual computing units are activated in an on-demand manner to manage machine and deep learning requests made by users. Virtualization is provided by means of virtual machines or containers, and scalability is guaranteed by adding virtual resources for computation, storage, and networking exactly when needed, and by removing them when they are no longer required. In addition, thanks to these virtualization mechanisms, AI developers can design specific software environments endowed with AI toolboxes and frameworks, as well as AI applications. Examples of tools for this virtualization layer are VMware, Xen, KVM, HyperX, and Kubernetes. Let's move on to the second module, the computing framework. Computing framework is a software layer able to exploit the virtualization layer to support effective and efficient computation in a large-scale data center. Examples of computing frameworks are Hadoop, Spark, and Flink. Interestingly, computing frameworks available off-the-shelf differ in the employed technologies and provided functionalities, but we could generalize their architectures into 5 main modules: cluster manager, data processing engine, data storage, graph computation, and shells for programming languages. The cluster manager is the lowest layer interacting directly with the virtualization layer to manage the allocation and coordination of the processing that is distributed on different computing units, either virtualized or physical. The cluster manager typically relies on a scheduler, which is a software management module close to what we have in our operating system to coordinate the processing running in personal computers. Examples of this scheduler are Apache Mesos and Hadoop Yarn. The data processing engine is the software module responsible for the processing of the data. This engine is designed to operate in a distributed way by allocating, for example, the computation on a set of computing resources made available by the cluster manager and by integrating the results if needed. For instance, when we need to compute the mean value of a large-scale dataset, we could parallelize the processing by allocating the computation on different workers, each of which operates on a subset of the dataset, and the data processing engine finally aggregates the computing mean values to provide the overall mean value of the large-scale dataset. Examples of the data processing engine are Spark and MapReduce. An effective and efficient storage of data is crucial to speed up both the training and the inference of machine and, in particular, deep learning solutions. Examples of data storage solutions for computing frameworks are HDFS, HBase, Amazon S3, Cassandra, MongoDB, and Spark SQL. These solutions are typically strictly integrated with the cluster manager and the data processing engine. In addition, computing frameworks provide ad hoc tools for the processing of specific data structures, such as graph, as well as support shells for high-level programming languages such as Python, Java, Scala or R. After the analysis of the virtualization layer and the computing framework, let's finally see machine and deep learning frameworks, which aim at providing machine and deep learning solutions and algorithms for the AI application. In particular, machine learning frameworks provide AI methods for classification, regression, clustering, anomaly detection, as well as solutions for data wrangling and data preparation. These frameworks may or may not include neural network algorithms. Differently, deep learning frameworks are specifically designed to deal with deep neural networks that are specific types of neural networks characterized by a large number of hidden layers. Machine and deep learning frameworks can operate either on top of computing frameworks or as standalone solutions. Examples of machine learning frameworks operating on top of computing frameworks are SparkMLlib, BigDL, and Mahout, while TensorFlow on Spark, DeepLearning4j, and BigDL are examples of deep learning frameworks operating on top of computing frameworks. Differently, examples of standalone machine learning and data processing frameworks are Scikit-learn, Torch, Pandas, NumPy, Matplotlib, while deep learning frameworks meant to operate in a standalone manner are TensorFlow, Caffe, MXNet, Keras, Theano, Microsoft CNTK, and PyTorch. Interestingly, deep learning frameworks are typically able to exploit hardware accelerators such as GPUs, TPUs, and FPGAs, while standalone solutions are typically organized into shells and libraries. Summarizing, when the AI hardware layer refers to data centers, the intermediate AI software layer comprises the virtualization layer, computing framework, and machine and deep learning framework. Finally, the upper AI application layer refers to machine and deep learning as a service. Such a novel technological paradigm will be explored in the next video. Stay tuned!